Hello, welcome to my talk on approximately counting independent sets of a given size in bounded degree graphs. My name is Ewan Davies, and this is joint work with Will Perkins. An independent set in a graph is a subset of the vertices which spans no edges, and the complexity of counting and sampling independent sets has received a lot of attention in computer science. This topic combines insights from several areas, including combinatorics, statistical physics, the geometry of polynomials, and of course, algorithms. There are many related spin systems in statistical physics, and our ideas surely apply to other problems. But I'll focus on the example of independent sets for this work. So to count independent sets, I'm going to write IG for the set of independent sets in a graph. And an important object here is the independence polynomial, which is this function zg lambda, defined as the sum over all independent sets in the graph of lambda raised to the power the size of the independent set. This is also known as the partition function of the hardcore model from statistical physics, and that's going to be crucial in our proofs. Natural counting problems for independent sets are sharp P hard in general, so we focus on approximation algorithms. In fact, we have a detailed understanding of the complexity of approximating the partition function in bounded degree graphs. Turns out there's a computational threshold that coincides with a probabilistic phase transition of the hardcore model. And I'll explain what that means when we get to the details. So what does this computational threshold look like? The notion of approximation that we're interested in is that of a fully polynomial time randomized approximation scheme, or FPRAS, which is a randomized algorithm that with probability at least 3/4 outputs a number within a factor e to the epsilon of the solution to the counting problem in time which is polynomial in 1/epsilon and the size of the input. And for this talk, the inputs are graphs, so the size of the input will be the number n of vertices. And just to be precise, when I'm quoting previous results, an FP-TAS is a deterministic version of this kind of approximation scheme. To set up the problem, consider a maximum degree parameter, delta, which should be at least 3, and look at the problem of approximating the partition function zg lambda over graphs of maximum degree delta. The computational threshold turns out to be the lambda critical value, which I've given here. And for subcritical lambda, there's an FP-TAS for approximating the partition function due to White's. And there's a hardness result saying that unless NP equals RP, there is no FPRAS for lambda when it's bigger than lambda critical. This is due to Sly Sun and Galanis Stefankovic Vagoda. And let me just point out that this assumption, NP not equal to RP, which leads to the hardness result, is pretty standard in complexity theory. And it basically means that we assume that randomized polynomial time algorithms cannot solve all problems in NP. Actually, this threshold lambda critical was long known to be what's known as the uniqueness threshold for the hardcore model on an infinite delta regular tree. So the value itself was long thought to be important to what's going on with the hardcore model, but it's nonetheless very interesting to have this confirmed in the computer science literature. I'll explain a little bit about what that uniqueness threshold means when we look at the hardcore model in detail. So in this work, we affirmatively answer the natural question of whether there is a similar computational threshold for the problem of approximating the number of independent sets of a given size. So let's look at this in a little more detail. We can write IKG for the number of independent sets of size k in a graph G, and observe that these IK things become the coefficients of the independence polynomial as a polynomial in the parameter lambda. And given a density parameter alpha, we considered the problem of approximating the number of independent sets of size alpha n in an n vertex graph G with a maximum degree delta. And we have to do a little bit of rounding there to make sure that alpha n is an integer, but that doesn't affect the analysis in any way. So a little bit like on the previous slide, we identify a critical density, which is asymptotic to e over 1 plus e times 1 over delta, as delta tends to infinity. And we give an FPRAS for IKG when k, as the given size of the independent set, corresponds to a density, where density is alpha n, with alpha less than the critical value. And we show that unless NP equals RP, there can be no FP-RAS for alpha larger than alpha critical. So this establishes a computational threshold, much like is known for the lambda parameter in the case of approximating the partition function. In more detail, actually, we focus on an approximate sampling algorithm. So we give an almost uniform approximate sampler for independent sets of a given size, when that given size has a subcritical density, and the counting algorithm follows by a standard reduction. So I won't give the details of that in this talk, but it's a well-known fact about these sampling and counting problems is that often there's a good equivalence between the two problems. And I've put here the exact value of the threshold alpha critical at delta. And just in terms of a function of delta, it's not particularly illuminating what we have there, but it is interesting to look at this as a function of the critical lambda for the similar problem of the partition function. It turns out that this formula naturally arises by the solution to an extremal combinatorics problem over the class of graphs that you consider for the approximation problem. So this alpha critical that we get is due to the fact we're looking at bounded degree graphs, and there's an extremal combinatorics problem we solve to get this threshold. We also show that restricting the problem to triangle-free graphs, which then gives a slightly different combinatorics problem, results in a different threshold. And we don't determine this threshold exactly, but we show that as delta is tending to infinity, this threshold is asymptotic to 1 over delta, which, if you recall, is a little different from alpha critical, which is the general case for bounded degree graphs. I'll point out here that this work motivates the further study of previous methods for sampling independent sets of a given size. One particularly nice one is based on Markov chains and has been used since the 90s. And this is not currently known to yield efficient algorithms for sampling and counting for densities larger than 1 over 2 delta. So these new algorithms from this work are performing efficiently at higher densities, and it'd be very interesting to understand better the limitations of the Markov chain-based approach. I should point out that there's a lot of related work in the literature, and the sampling techniques that we employ have roots in the seminal works of Jerram and Sinclair, who are looking at some of the same kinds of counting and sampling techniques and equivalences that we employ. And much more recently, Harris and Kolmogorov studied the general problem of approximating the coefficients of partition functions. So this is a more general definition of partition function, of which the hardcore model is an example. And in their framework, they needed access to a sampling oracle, which involves, it's the equivalent of having access to samples from the hardcore model. And they looked at optimizing the running times quite carefully, and you could certainly slightly improve the polynomial running times of our algorithms with some of their ideas. I should also point out that approximating IKG has arisen in parameterized complexity. And for example, it's known to be fixed parameter tractable in bipartite graphs. So on to the details of our techniques. This is where I want to define the hardcore model and discuss some of the statistical physics, which actually informs the methods we use in the paper. So the partition function ZG lambda defines a probability measure, mu lambda, on the independent sets of the graph, where the probability of any given independent set I is lambda raised to the size of I divided by the partition function. So this is just a probability proportional to lambda to the size of I, and the partition function is a normalizing constant to make the probability sum to 1. So this is the hardcore model, and it's an example of a Gibbs measure and the grand canonical ensemble from physics. And it turns out that in physics, there's a related idea known as the canonical ensemble. And these two things differ. They're statistical models of systems like gases in a volume. But in the grand canonical ensemble, you suppose that the system can freely exchange particles with an infinite reservoir of particles. In terms of the hardcore model, we see this in the way that the set sampled from the hardcore model could be of any size, from 0 to the maximum possible size in the graph. And since the vertices in the independent set correspond to the particles in the statistical physics model when you're studying these things, this is the phenomenon of exchanging particles with a reservoir. So if you want to consider a closed system which cannot exchange particles, then this is the canonical ensemble. And in the case of the hardcore model, this is the uniform measure nu k on the independent sets of a given size k. So in physics, the ensembles are known to be equivalent in some respects under certain conditions, and we exploit this general idea in our proofs. So how does the approximate sampling algorithm that we give work? It's based on a very simple idea, which is that one way of sampling from the uniform distribution on independent sets of a given size k is to pick a lambda, and in fact, any lambda, any positive lambda will do, and sample from the hardcore model at that lambda until a set of size exactly k appears. Now, the structure of the hardcore model means that conditioned on getting a set of size exactly k, we precisely have the uniform distribution on the sets of size k. So the devil is in the details of whether you can do this efficiently. So we prove that this is efficient when the density of the independent set that you're looking for is less than alpha critical. And there are two key ideas in our approach. The first is a search over lambda values so that we can find a lambda where the expected size of an independent set from the hardcore model at that lambda is close to the desired size k. We implement a binary search to make sure our algorithm is reasonably efficient, but basic linear search is fine if you want a polynomial running time. Once you've done that, you need to keep sampling at this good value of lambda until you get an independent set of size k. And to understand how efficient that is the same as understanding the probability of getting size exactly k when you're sampling from mu lambda. And this part of our proof is quite interesting because to establish a lower bound on this probability, we actually use several recent advances in the geometry of polynomials and in the rapid mixing of Markov chains for the hardcore model as a probabilistic tool to lower bound this quantity. So we don't actually need to do much with the geometry of the hardcore model as a polynomial, but we use known zero-free regions for that to establish certain probabilistic results. So for this sketch to work, it's crucial that k is close to the expected size for some lambda that we can find, because we prove that the hardcore model is somewhat concentrated about its expectation. And so if you choose a lambda where k is very far from the expected size, you're unlikely to get that k. What's also important is that the lambda value that you find, which results in an expectation close to k, needs to be subcritical, because the way this sketch works is that we are sampling from the hardcore model until we get a set of the right size, and we need to do this efficiently. So to do that, we're going to use the approximate samplers for the hardcore model, which exist from several different results. And they won't work if the lambda is supercritical. So it's exactly this constraint which gives rise to the extremal problem that determines the critical density alpha c. So if you go through the details of this, you'll see that what we need to do is minimize the expected size of an independent set from the hardcore model over graphs of maximum degree delta, and a fixed number n of vertices. So I don't have time to go into the details, but I just want to highlight that that's where the extremal combinatorics problem comes in. So this sketch shows roughly how our approximate sampling algorithm works, and there's a standard simulated annealing technique which has been used many, many times for turning this into an approximate counting algorithm. The other side of the coin is that we want to show that approximating the number of independent sets of a given size is computationally hard when the density is larger than the critical density. And to do this, we reduce the problem of approximating the partition function to the problem of approximating just one coefficient, this ikg. The construction is very simple. We actually take a graph G and add many, many copies of a small graph. It's convenient for technical reasons to choose that small graph carefully. but you get most of the strength of the result just by considering a delta regular clique. So it's a good concrete example. So we let G prime be the original graph G together with many, many, many copies of a delta regular clique. This new graph is still of maximum degree delta, and you can do a calculation or appeal to some nice probabilistic results relating the canonical ensemble and the grand canonical ensemble to show that approximating ik in the bigger graph G prime gives access to an approximate value of the partition function of the hardcore model on the smaller graph. And of course, the lambda value of that hardcore model that you get access to is a function of the given size k that you look at in the larger graph. And if you go through the details of the calculation, it turns out that when alpha is supercritical, and this given size k is at least alpha n, then the lambda that you're simulating on the small graph will be supercritical itself. So by the previous results that I mentioned for hardness of approximating the partition function of the hardcore model, we've reduced a hard problem to approximating number of independent sets of a given size. So that's how our hardness proof works. And I think this work raises some interesting questions for future research. So one natural one is that our algorithm is inherently randomized because we use the approximate sampling scheme to obtain a counting algorithm. And it would be very interesting to develop deterministic techniques for approximating the number of independent sets of a given size. I'll mention again this natural Markov chain, which walks the independent sets of size k. The transitions of this Markov chain is to take the uniform random vertex in the current independent set, remove it from the independent set, and then transition to a uniform random extension of this smaller set back again to an independent set of size k. So this is known as the down-up chain on the complex of independent sets in the graph. Currently, by spectral techniques, this is known to mix rapidly when k is at most n over 2 delta, which is density 1 over 2 delta, recently analyzed by Alev and Lau. But we think this could be improved to the critical density. So that's a conjecture from our paper. Then a couple more points which are more to do with the probabilistic details of our proofs. I mentioned in the second key point that we needed to lower bound the probability that we get a set of close to the expected size from the hardcore model. And the techniques that we used were relatively simple and gave a lower bound of roughly 1 over n log n on this probability. We actually conjecture that a much stronger bound, 1 over root n, should hold. And the intuition for this comes from actually believing that a local central limit theorem should hold for the size of an independent set drawn from the hardcore model on this subcritical range of lambda values. So our work on algorithms kind of motivates this more detailed probabilistic understanding of the hardcore model, because the links between the hardcore model and the fixed size, uniform measure are quite interesting, and we've applied them to design algorithms. So it'd be good to develop a deeper understanding of these topics. Thank you very much.